is the video tutorials on how to construct workflows with Scipion3, and we will use for that an Apoferritin example taken from Empire. The code is 10,248, and we will divide this tutorial into a few pieces. The first piece will be to import the movies and then process the movies, estimate the Ctf, and produce micrographs that we are happy with. Second one will be choosing our particles in the micrographs and then cleaning those particles, doing some 2D processing. Then we will construct an initial volume. This is this block in green. Then we will try to get an homogeneous data set and reconstruct it to a high resolution. And then we will use some validation tools to make sure that what we have done is the right thing, and we will interleave validation tools with further reconstruction and refinement of our structure. So here in the left we have the possible operations that we can perform with Scipion, and I don't have installed all of them, but if you want to install more, then you can go to the plugin manager. This is the project window of Scipion. You can go to the plugin manager, and here in the plugin you can have access to the different possibilities. So they are grouped by software packages. So XMIP is one of them, then Relion, Iman, or any other one. And here you have in bold the ones that can be updated. So there is a new version of the CryoSpark 2 plugin since I installed it last time, and there is no new version of Iman 2, for instance. And under each one of the plugins you can install different binary versions of that package, and in principle it should be as easy as choosing it and then installing. And also in the same way you can uninstall, so you can uninstall it in this way, but I will not do it. Okay, so let's go back to our example. So the first piece of the tutorial is how to go from movies to micrographs. So first we import the movies, and here the important parameters is where the movies are, which is the extension of those movies, and then if there is a gain image, which one that is. If there is a dark image, the gain and dark images will be applied to the whole acquisition. And then what is the dose per frame, what is the microscope voltage, and spherical aberration, amplitude contrast. You can further refine it with XMIP, but this is not too much tested. So typically people take just the constant value for most of their projects. And if you want to correct for the dose at the beginning, then it is important that you give it here. But my personal impression is that it is better to do it at the end, in the polishing steps. Once you know the structure, then you can refine it with, or you can refine what is the weight of each one of the frames once you have information about how the structure looks like. Otherwise, for me, it is a little bit dangerous. The other important, really important parameter is the pixel size, because if you make it wrong, if you give it wrong, then all the default key and everything will be incorrectly computed. Then we estimate what is the movie gain. So the movie gain, the parameters is what is the set of movies that you want to apply it for. So actually, if you look at every one of these boxes, we call the boxes protocols. So each one of the boxes has an input and an output. The first one is the only one that doesn't have an input object, but the output. So every box produces some outputs of some types. So this is a set of movies. This is the name of the output label, if you want. So it is called output movies, but the important thing is this set of movies. This is the type of that output. And then every new protocol has an input that is this set of movies, for instance. So it has a type as input, and it produces outputs of different or the same type. So the movie gain estimates what is the gain of the microscope, and for instance, this one, the important input is mostly what is the set of movies that you want to estimate, and then you can estimate what is the gain orientation, because sometimes it is flipped by 90 degrees, it is rotated 90 degrees, or it is flipped in X or Y, and then we will also estimate what is the residual gain. And actually, if you go to the browse, we cannot see the gain. We cannot see through the analyzed results, but you can go into the directory of that execution and then see. So this is how the original input gain looks like. So you see here the polishing effect, and after correcting the polishing, what we see is that still there is some residuals. So these residuals, we can see them here. So this residual gain should be ideally 1. In this case, it is not the case. So I think we could have done a better gain estimation. And you see that it is mostly centered around 1. So the mean here is 1, but the standard deviation is significantly different from 0. So it is, in practice, it is never 0, but it can be rather concentrated if you do a good gain estimate in the microscope. And then these movies here, this set of movies, has attached the reoriented input gain, not the residual gain. And then we will go into the flex alignment. So the flex alignment is one of the operations that you can do for aligning frames into a micrograph. So the original ones in XMIP was motion correction. That was only a global correction. Then we had the optical alignment, and now we have this new version of flex align that goes on GPUs, and it is more accurate and more general than the optical alignment. And then you have alternatives like rely on motion correction, system, and blur. You have also motion core 2, although I have not installed it in my computer. This is a laptop, and I don't have it there, but we have it in some of our clusters. So I use this flex align, and the output of this is so it is a micrograph that we can see now the particles. Otherwise, in the movies you barely see anything. We can see how the input data looks like. So this is the, let me see if we can open. I think it is opening. Yeah, that's it. So we can try to enhance the contrast just to see something, and then zoom in. So this is how the data looks like originally. So it is just a set of points, and these are the electron hits in the detector. So we have 50 of these frames, and what we have done is to align them, and the important parameters to align them is what is the resolution, that there is a low pass filter in between. So this low pass filter is controlled by this maximum resolution, and if you have very few uh, detections, very few electrons per pixel, then you may want to increase this value. And the other important parameter is whether you want to sum all of the frames together, or you want to just from 1 to 20 to avoid the more damaged frames. Although this calculation of what is the weight, the relative weight of each one of the frames, I think it is also better done at the end, at the polishing point. And then otherwise most of the parameters you can keep them as they are. So we have seen the micrograph. So each one of these circles is an Apoferritin image, the projection of one of the molecules of the Apoferritin. And then we also have estimates of what is the shift from starting from image 0 or image 1, and then it goes 1, 2, 3, 4, 5 up to 50. And we can see that here in pixels we are moving like 30 pixels. 30 pixels is 15 angstroms, because I remind you that the pixel size is 0.5 angstroms per pixel. So and something that would be very useful would be to compare different outputs of different motion estimation algorithms, just to make sure that these shifts are correctly estimated. So these are global shifts, but so this is a kind of summary for each one of the frames, but the shift estimate is actually local. So at every pixel it is estimated a local movement. And the other thing that you may want, or you should want to look at, is the power spectrum before and after alignment. So before alignment, you see here that there is a drift. So these tone rings are fading in this area, and that is an indication of drift. But then after alignment, we don't see this drift any longer. So the drift has been corrected, and then the tone rings add up coherently in Fourier space. So you should see always the tone rings better in the motion corrected image than in the non-motion corrected image. And then we have a protocol that puts some of the movies aside, and according to some criteria. So you can take the aligned movies and then put aside all those movies that has a single frame shift larger than 5 angstroms, or the whole movie shifts more than 20 angstroms. And we can see that in this particular case we only started with 30 micrographs. The whole data set is much bigger, but just for a tutorial and to finish on time, we have taken only 30 of those movies. And then 29 of them met our quality criteria, but one of them didn't. And we can see why this one didn't. So for instance, here, if we analyze this one, or maybe it is here. No, we cannot see this shift estimation is not propagated, but one of them didn't meet this maximum frame shift. And okay, so then we go to the Ctf estimation, and we will do for that we will try to get good estimates of what the CTF look or the defocus is, and for that we will use two programs. One is Ctf Find 4, the other one is Ctf. So they have different properties, and each one has different mathematics and implementation, so there can be considered to be independent estimates, and each one of them computes different things, and some of the things are actually common, like the defocus is common. The defocus ratio is something that Scipion is computing. The resolution reported by the program, and this fit quality, and then we have representation of what is the estimated CTF with respect to what is the experimental power spectrum, and they should match. So all the rings should match up to high frequency. So here it is hard to see. So we see that the first ring is matching very well, but from that point on it is relatively difficult to see whether they match or not. Here they match probably, but sometimes it is difficult, but it depends on the data set. And the same for the other one. So for the other one we don't have in this case the representation of the matching, and we have again the defocus ratio, resolution, and so on. So now what we will do is a consensus between the two. So here we will have a primary Ctf estimation. So the primary in this case will be Ctf Find 4. You can take any one of the two, and then you can put some criteria on the Ctf Find 4 on the primary. So for instance, the defocus has to be between this range, in this range. The maximum astigmatism must be this one. The resolution must be better than 4 angstroms, and then we have not used any of the we have not used XMIP Ctf estimation, so we cannot use the XMIP criteria. And you have the other consensus, the secondary estimate, and the secondary estimate we have GCTF, and they have to agree, the primary and the secondary, up to 4 angstroms. And for those columns that are in common, for instance the defocus, we will compute an average. So that is actually a very good way of getting rid of estimation errors. So each one of the methods, disregarding of whether the CTF fitting looks relatively good or not, it is much more accurate if you average their estimates, because all the parameters have a random error on top of it, and then by averaging you are reducing that random error, and then you are also taking all the uncommon variables, so all the columns coming from the Ctf Find 4 or GCTF that are not in common, then you are also adding them to the output. So the output, for instance here, one of them was discarded, and the reason was resolution. So that micrograph didn't have a resolution better than 4 angstroms. Then once we have a good estimate of the defocus, we can go for an estimate of the envelope, and XMIP is estimating the envelope, and since we think that we have a better estimate of the defocus, then we will not optimize the defocus. So we will take the output from this consensus, and we will estimate only the remaining parameters, and in XMIP those are referring to the envelope. And here is an interesting wizard. So this wizard tells the algorithm where to look for the fitting. So we will fit within this blue area, and then this is between 20 and 2 angstroms in resolution, and yeah, so we will do that fitting, and then the output looks like this. So it is not only that we are estimating the defocus. The defocus is already given by the previous consensus, but now we are also estimating the decay of the rings. So in principle, this decay in the theoretical part should look like the decay in the experimental part. And there are many parameters that we also compute. So some of them, for instance, what is the correlation between the first and third zeros of the Ctf? What is the first zero of the Ctf? What is the iceness? The iceness is defined as the ratio between the power at 3 angstroms resolution, that is the frequency or the resolution associated to ice, to an ice crystal, or even if it is an amorphous ice, it can diffract quite a lot at 3 angstroms, and the ratio between 3 angstroms and 4 angstroms. So if that ratio is smaller than 1, that is an indication that there is no ice. And then up to which frequency you have 2 defoci. So one is in one direction, the other one is in a perpendicular direction. And what is the resolution at which these 2 defoci start to be inconsistent with each other? And inconsistent means the correlation between the Cdf waves is smaller than 9. So there is a phase shift of more than 90 degrees. And then, so you would like this non-astigmatic validity to be very high. You can also make histograms of those, for instance. So we can check what is the histogram of the non-astigmatic validity, and also what is the histogram of the resolution. And the definition of resolution for XMIP is different than that for the other programs. For the other programs, normally they look at which frequency the estimation of the Ctf and the experimental one differ or do not correlate any longer. So for us it is at which frequency there is no more energy, and we see that there is no more energy somewhere between a little bit beyond 3 and 2 angstroms, depending on the micrograph. And the non-astigmatic validity is also relatively good. It is between 3 and 1. So we see that for most of the micrographs, so this data set, as it is now, it will be limited to a resolution between 3 and 2, most likely. And because of resolution, because of non-astigmatic validity, and also we can see what were the estimates before. So we didn't look at it, but this is also a very good estimation of sorry, so I want to see which are the micrographs. No, not the micrograph, but the Ctf. And then we can see the histogram of resolution. So according to all programs, this data set is limited around 2.5 to angstroms resolution. So actually there is a trick here. The trick is that this data set was acquired with beam tilt, and then the beam tilt limits the resolution to that frequency. And if you correct for the beam tilt, you can get farther, but otherwise you cannot. Okay, so then we will finally compute another consensus, and this consensus this time will be between the GCTF and the so here we have the consensus between GCTF and CTF4, and we have similar setup for the remaining parameters. The primary now will be the XMIP Ctf estimation, and that is because we want to use the XMIP criteria to filter the data. So the minimum of the first zero is 5 angstroms, and this is because sometimes some of the programs make very bad estimations, and then the first zero goes to some crazy value, and then this is the maximum astigmatism in the first zero, so we allow for a variation of 10% in the first zero. What is the minimum correlation between the first and third zero? The CTF margin encodes how visible the tone rings are. So the more visible they are, the larger the CTF margin would be. And a CTF margin of 1 means that the second tone ring is 1 standard deviation above, or has the same standard deviation like the noise, and then so that is not a good indication. And then the maximum iceness, so this iceness criterion, if it is larger than 1, there is a bit of ice, so we allow for up to 5% of ice. And the non-astigmatic validity, they have to be between these two values. And well, so the point here is that you can compute, you can, after this alignment or this movie alignment and CTF estimation, you can be pretty sure that the foci that you have computed is good, and that the micrographs passing through all these filters, they at least they don't have any pathological behavior. So we can see, for instance, which are the CDFs of those micrographs. So we can see that most of them, they have a good appearance. So sometimes you don't see rings, sometimes you don't see or you see that there is a drift that was not correctly estimated. And with all these filters, you can be pretty sure that the micrographs you have selected are the right ones. Okay, so let's stop the tutorial here, and then we move on to the next block of the tutorial in the next video.